All right, so your third assignment is out, and due Thursday and Friday. Any questions about it or anything else? Yes?
Are we supposed to be able to solve it with what we know right now? Or
Yes, you should be able to solve it with what you know right now. Yes?
So in the master theorem, when you're determining the setup cost for the algorithm, so you have like plus something, can you throw out constants?
Okay, so we ask when you're trying to determine the cost, you're using the master theorem, so you're trying to account for the non-recursive part of the cost. Can you throw out constants? Okay, so I've gotten a number of questions very similar to that, so let me address that. So suppose you do a really great job of analyzing a recursive algorithm. You decide, okay, the cost of dealing with the problem of size n is equal to 2 times the cost of n over 2 plus, and then you decide it's like 3.752n minus 1.987 log n plus 52, for whatever reason. Can you use the master theorem on that? Because that sure doesn't look like anything that shows up in the master theorem. Okay, how can I use the master theorem? Yeah?
So, like, we don't really care about the constant, and the coefficients we can basically ignore as well. And log n isn't very small, or isn't very large compared to n as it gets bigger. So, like, for me, like, I would just put n.
Well, in fact, if you say n, if we just replace that with n, so she gave an argument about what we could throw out and disregard and simplify it to n, but that still doesn't look like the master theorem to me. Yeah, back there. Yeah, no.
Okay. So it'd be big O, and you want to put an upper bound on it.
Okay, right. So, same idea. But the master theorem, you expect to see on the right-hand side O of some polynomial, n to the d. So always, when you're applying the master theorem, you look at what's over here. And to apply the master theorem, you just got to you've got to find a bound that you can express. Whatever you've written right here has to be O of n to some power d. Okay? So and the smaller the d, the better. So what d should we use here? Yeah. So this just turns into plus O of n to the 1. And then you can apply the master theorem. So whatever appears after that plus, just put a big O bound on it of the form O of n to the d, and then you can use the theorem. Now what if you said plus O of n to the 4th? That's true. The thing in the box is O of n to the 4th. What would happen if you used the master theorem? Would you get a wrong answer? Yeah?
It wouldn't be as accurate. You're asking for the tightest bound possible.
Right. So what he said, it wouldn't be as accurate. It would still be correct. You would get an upper bound. In this case, the upper bound would be O of n to the 4th. That's true. The algorithm we've described is O of n to the 4th, but that's not the tightest bound possible. So you'd want to, that's why you'd want to use O of n to the 1st. Yeah?
If on the right side it's like O of the n log n, then what is the d? Would that be? Like if it was n squared log n?
Mm-hmm. So if on the other side it's plus n squared log n?
Yeah.
Well, let's see what would work. Is that O of n squared? No. Is it O of n cubed?
Yes.
Okay. Is that the best we can do?
2 plus epsilon.
Yeah, we can make, the bottom line is that this term right here, n squared log n, is O of n to any exponent that's bigger than 2. The reason being that log n is O of n to any positive power. Any polynomial grows faster than any log. So d doesn't have to be an integer. You can,
Yeah. When you say tightest up or down, like, I'm kind of curious why we keep dropping the low order terms when we want to like keep tightening them down.
Well, he's asking why do we keep dropping the low order terms when we want to keep tightening the bound? Well, we want the tightest big O bound possible. And big O doesn't care about leading constants or low order terms. Any other questions? Yeah?
Where epsilon is greater than 0.
Yeah, epsilon has to be greater than 0, no, it has to be positive. Okay, now I'm going to head off some potential problems. So, the caddis problem. Okay, so in the caddis problem, the way the problem works is you imagine a universe full of stars, and the universe has a constant, V, which is the galactic diameter. So imagine you have, the way the universe as you get as input will be structured is there are a bunch of stars organized into galaxies. And what property does the universe have? Well, it's two-dimensional, that's true. Well, yeah.
Stars in different galaxies will be greater than the galactic diameter
Apart.
from each other.
Okay, so stars in the same galaxy, any pair of stars in the same galaxy will be within one galactic diameter. And stars that aren't in the same galaxy will be more than a galactic diameter apart. And this isn't really drawn to scale here, so let me reduce the diameter here. So if two stars are within d of each other, they're in the same galaxy. If they're more than d apart, they're not in the same galaxy. That's nothing you have to check. You're given d, it's just a property of the universe. You won't get a universe where two galaxies are close together, so you couldn't have something like this. Right? There's no way to turn, there's no way to invert that. That's illegal. If we make this chunk here one galaxy, there are stars in the same galaxy that are too far apart. If we make them into two or more, there are some stars in different galaxies that are too close together. Okay? This problem is constructed so that you pretty much have to solve it with the majority algorithm, like we talked about last time. Yep.
Can you explain that you don't have to validate the input?
I already said that, but I'll say it again. You don't have to validate the input ever in a caddis problem. If you're spending time in your code checking to make sure that the input meets the constraint stated in the problem, you're wasting your time. They'll be correct. So you don't have to worry about the validity of the input. Just the validity of the output. That's your problem. So if about any other approach, I've peeked. I've looked at what people are doing on caddis, and I will see nested loops that are running out of time. You do not have time to sort the stars into galaxies. There are too many stars in some of the test cases. So the problem is to determine is there a galaxy that has more than half the stars? And so what people first think of is, okay, I'll just make a list for each galaxy. I'll find a star. If it's not part of a galaxy, I'll put it in its own galaxy. And gradually organize the stars into galaxies and then see if one of them is bigger than half of the stars. You don't have time for that. I don't care how clever a programmer you are. So you need to use a majority algorithm like we were discussing last time. What's that?
What the complexity of that, the n squared?
Yeah, so what I just described would be an n-squared algorithm, that you have nested loops that are sorting them into galaxies.
So you can have a whole bunch of single stars that are their own galaxies?
No, we don't need to. I think we've covered it enough here. So now, another thing I think might happen is you ask your friend, what's the caddis problem this week? And they say Galaxy Quest, and so you go to caddis and start working on it. What step have you skipped if that's how you started?
Log in, so we get your
Reading the notes on Canvas.
Reading the notes on Canvas, he said. I know from experience that just reading the problem description on caddis, a lot of people won't really understand what's going on. I put lots of hints in Canvas So go to the problem on Canvas and read that as well. That's where you find out not to try to use an n-squared algorithm. Okay, any last questions? Okay, speaking of majority elements, or majority algorithms, we were discussing the problem last time. And so what I had you think about is to devise a divide and conquer algorithm that returns the majority element of an array, A, or reports that it doesn't have one. And this is, I forget exactly how far we got discussing this, so I'll just start over with it. You're asked to find the majority element of an array A. If the length is 0, there's no majority element. If the length is 1, then that one element is more than half of more than half of the array, so you return it. Otherwise, we split our array into halves, A1 and A2. You find the majority element of A1 and the majority element of A2. Now, the possible return values are, find majority, either return an element, that's a majority element, or return no, saying there is no majority element. The key idea here, there's always a key idea in any divide and conquer algorithm. What's the key idea here that makes this work? Split the array in half, and based on what you call the algorithm on the two halves, and based on what you get back. Yes?
If there is a majority, it will be the majority of either the right or the left side.
Okay. So if A has a majority element, it'll have to be the majority of one of the halves, if not both. Okay? You have to think about that for a while to convince yourself it's true. But if I've got some element X that is more than half of the elements in this array, and I split the array in half, X is going to have to be in the majority of one of the other arrays. So that's the key idea. So what we do is, when we get our answer back, if X and Y are both no, then A doesn't have a majority element. Right? The only possible majority elements are the ones returned by X and Y. So if they're both no, we return no. If X is no, we can't say X is a majority element. I mean, we can't say Y is a majority element, but we have. So what we do is we verify it. We count how many times Y occurs in the array. If it occurs more than half the time, it's a majority element. We return Y. Otherwise, we return no. This case is symmetrical, and otherwise, if we get two different numbers returned, X and Y, we have to check both and see if they're a majority element. So essentially, we're using these calls to get the only two possible candidates for being majority of the overall array. We check each one out as necessary, and if one of them pans out, we return it as a majority element. Okay, why do we have to check? Suppose we have an array and we find out 7 is the majority of that half, and there is no majority of that half. Why do we have to check to see if 7 is really a majority element?
You could have no more 7s in the other half, in which case you would have less than a majority in the total array.
Exactly. We could have started, say, with a 10-element array, 6 of them are 7s. When we split, all 5 7s are in one half, and there are 5 7s in one half, and only 1 7 in the other half. That's wrong. You could have started with 5 7s in an array of length 10. All 5 end up in one half, and none in the other half. So 7 is going to be reported as a majority element of the first half, but it's not a majority element of the entire array. So we just do a scan through to count them. So that's an algorithm you could use for Galaxy Quest. How complex is it? Hopefully, presumably it's not n squared. So let's think about it. How many recursive calls are we making? 2. How big are the two halves? N over 2. And then what is the work we're doing?
Linear.
Okay, so we're doing this division into halves. That's going to be a linear amount of work, depending how we do it. Counting, counting the occurrences of y, that's going to be linear. You know, counting the occurrences of x, whatever we have to do is a linear sweep. So there we have it. 2 recursive calls, each half the size of the original, plus a linear amount of work. So we get that, and by the master theorem, it's n log n. So that's an n log n algorithm, much better than an n squared algorithm. That'll solve that majority problem. Okay. We're going to look at a faster one. Are there any questions about that before we move on?
And addition takes constant time, right?
Addition takes constant time?
Because when we're counting.
Yeah. But, you know, we're not talking about arbitrary length integers. Yeah. Addition will take constant time. Okay. Here's another one. So here's the start for this. You take the n-element array, you divide them into pairs. So you just pair off the elements. And if there's a leftover element, we'll call it y. Discarding it, I shouldn't have said we discard it. We're going to keep it and use it later. We don't use it right away in the recursion. And so you pair them off. And if you look at the elements in each pair, if they're the same, you keep one of them. If they're different, you discard them. And now you've got an array A prime. What can we do with A prime?
Find the majority of that.
And he said find the majority of that. Let's let me show you what I'm talking about here. So I'll save this away. All right, suppose this is our array. 1, 5, 2, 1, 3, 3, 6. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I don't have a majority element yet. So I'm going to change this. Okay, so there are 5 ones and 4 other things. So 1 is a majority element. So what I'm talking about is pairing off like this. So if the pair is, if it's different, I throw both away. If they're the same, like this 1, 1 here, I carry 1, 1 down here. I get a 3 down here. And that's what I get with the 1 left over. Now, the way this divide and conquer algorithm works is we now recursively find the majority element of that thing right there. And it turns out that the majority element of the overall array will either be the majority element of that array or the leftover element. There are only 2 possibilities to consider. Either that odd element is a majority element or the majority element may be whatever is returned by that recursive call. Now, what will be returned by the recursive call in this case? When we ask for the majority element of this array. No, there is no majority element. And so what we do is we find that, okay, the recursive call did not return a majority element. So we're going to screen 1 and see if it really is a majority element. So we'll count ones and we'll find out if it's a majority element. Now let's change the situation a little bit. Suppose that instead the 1 occurred there and the 6 occurred there. What would, so let's do it over here. What would happen when we scanned through it, looked at the pairs?
1, 3.
We throw both those together. We'll keep a 1 here. We'll keep a 3 here. We'll keep a 1 here. And our leftover element is 6. So when we ask to find a majority element of this array, what's the answer going to be? 1. And then we'll double check and make sure 1 really is a majority element by counting the ones in this array and find out that it is. So you might wrestle a little bit about why this pairing up idea works. Why does it seem like it could work? What is it about pairing up? Yeah?
If
Because in the previous algorithm, down at our base case, there was a point at which if we did the previous algorithm on this array, we would get like a 1 or a 3, and then those would be returned up through the recursive calls at each step.
Yeah, so you're focusing on the recursion, but what is it about the pairing that gives us an array that has a property that we want? Yeah.
Well, when you pair them up with the majority element, you'll always have greater than a half. And so if you keep splitting those pairs up, you'll always end up with either that pair or
Okay.
the leftover.
So that's getting at it. So the odd leftover element causes a problem. So let's assume there's not a leftover element.
But you'll always have one greater than.
Yeah. So the majority element, you know, if you try to pair the majority element with things that aren't equal to it, you're eventually going to have to pair, say, the 1 with itself. And if two things that aren't majority end up being paired, that forces more 1s to be paired. That's the basic idea.
Pigeonhole?
Yeah, you just said pigeonhole principle. Yeah, there's only so many ways you can avoid pairing a 1 with itself. Yeah.
Could I give you a simple array to work through that I don't fully
Sure.
understand how it would work?
Yeah.
So, 1, 0,
1, 0,
1, 2,
1, 2,
1, 3.
1, 3.
The majority.
Okay, so there's no majority. Right?
Majority's.
It has to be more than half.
Oh, it's been more than half.
So let's see what the algorithm would do. So what would be the new array? The 1 and 0 are paired, so they're thrown away. The 1 and 2 are paired, the 1 and 3 are paired. So you'd find there's no majority element and there's no left over, so there's no possibility.
Okay, all right, that makes sense.
Yeah. But if you add one more 1 in here somewhere, like right there, no matter where you add the 1, unless it's at the very end, you're going to force a pairing of 1s.
Okay, and then if it's at the very end, it's just going to be the leftover.
Yeah, and the leftover is also a possibility of the majority element.
Okay, that makes sense.
Okay?
I have a question.
Yeah.
Which one works better for Galaxy Quest?
Which works better for Galaxy Quest? This one's faster. Which works better? I mean, which is easy for you to implement? I don't know. I don't know if anyone has an opinion. But whichever one you think is easier to implement, you can use. Okay, so let's let me save this. Okay, so let's analyze it.
So I'm sorry, just really quick before you move on. So it's basically, it's not a recursive algorithm because you're running through the list once. And
No, it is a recursive algorithm.
But you don't, so that's what I'm confused, guys. The new array that you just built is not, you don't do the same pairing method.
No, so you do that pairing, you build a list, and you want to know, you need to find out the majority element of that list.
Right.
So you make a recursive call. And that recursive call will pair up that list and make a recursive call until we bottom out. So yeah. So there's the algorithm. Again, if the list is empty, you return no. Else, if it's a link 1, you return a sub 0, just like before. Otherwise, you do the pairing like we talked about. So you find that a prime like we talked about, and we'll let y be the leftover one. You find the majority element of a prime with the recursive call, and then, there are various combinations of getting either there's a leftover element or not, and there's a number returned by the recursive call or no is returned. So there are all these cases to consider. But they all involve counting and pass through the array. Yeah?
So I know we're doing high-level pseudocode. I'm just trying to understand better. Like, you have some cases return no, and then some cases you're returning an actual element.
Right.
So how would that syntactically work?
Okay, so what would you do in a programming language? Because you've got to return either basically true or false. And if you return true, you've got to return a number as well.
So you return null or an often.
Some more.
Okay, so you can think of all kinds of ways to do it. Let's say you're using Java. You could return an integer object with a capital I or null. If you're using C#, you could, pass one of the parameters by reference, get it that way. Or you could return an object that contains two fields. Lots of ways to wrangle that. Let's analyze this. So how many recursive calls are we making?
Just one.
Just one. How big is each recursive call in the worst case? In the best case, it'll be empty. The recursive call will be an empty array if every element is distinct. In the worst case, how big can A prime be? Half as big. So what would that correspond to?
The majority elements of all the elements.
If you got one number in the entire list, right, then they'll all get paired up with each other, and the new list will be half as big. And then, let's see, the overhead is essentially the same as before. We've got to make a sweep through the list count. So it's linear. So we end up with that one. One recursive call, each half as big, plus a linear amount of work, and we get that it's O'd in using the master theorem. So it's a linear algorithm. Yeah?
The recursive calls on the line find A prime and Y is described above, or X equals find majority of A prime.
Okay, I somehow couldn't parse what you said, so try again.
I'm wondering where the recursive call is being made. Is it on the line that says find A prime and Y, or X equals find
It's
majority?
right here. We're calling find majority, right? Name of the method. So we make a recursive call to find majority. There's only one. So any divide and conquer algorithm that you devise or try to understand, there's always this, the notion, okay, we're going to divide the problem in half and solve it recursively, or divide it in thirds and solve it recursively. That's, it's easy to say, but you've got to have this key idea in mind. You've got to know how you're going to do the splitting, and once you get the results back, how you're going to combine them to produce the overall result. That's where the cleverness comes in, looking for that key idea. And we've looked at two different ideas here for this algorithm. So I'm about to move on from this. Any last questions before I do that? Okay. So we're going to finish up divide and conquer by talking about some algorithms that you're presumably familiar with in 2420. So we start with merge sort. So at a high level, this is merge sort. Let me get a pointer here. So this merge sort algorithm, we're given an array and a low and a high bound, so we're trying to sort the portion of that array between low and high. If high minus low is greater than or equal to 1, then we've got work to do. So we compute the midpoint between low and high. We sort the low half, we sort the high half, and then we merge them. So what is the recurrence relation that describes this in the worst case? Okay?
TFN is equal to 2 times.
Okay, so 2 times, because 2 recursive calls, you can see them right there, merge sort, merge sort.
TFN over 2
T of n over 2, because we're sorting halves,
plus O of n to 1.
plus O of n, because merge is linear time. Merge takes a sweep through both halves of the array and forms the merge. Okay, so let's see this in action. There's the array. So the way merge sort works is it conceptually splits the array in half. So there's our split. So we got the yellow and the brown. It makes a recursive call. And what happens when you make that recursive call?
Splits in half.
Okay, I just heard splits it in half. That is not the way I want you to think about recursive algorithms. There's a problem in this week's assignment where I do not want you to think that way. I want you to treat recursive calls, understand them by their specification. So I'll repeat. What happens when we make that recursive call in the lower half? Yeah, it sorts them. Okay? If you keep going through life thinking about recursion in terms of, okay, it splits it in half, splits it in half, splits it in half, splits it in half, then it hits the base case, and then it comes back up, and while it's coming back up, it does thus and such. Man, what intellectual overhead to understanding an algorithm. It's much easier to say, we split the array in half, sort the 2 halves, and then merge them. Okay? So we sort the yellow, we sort the brown, and then we merge. Now, merging requires an extra array. basically, we just sweep through the two halves. We compare the two halves. We see one is the smaller, so it's copied down. And we move over. 2 and 3, we get the 2. 3 and 4, we get the 3. 4 and 7, we get the 4. 5 and 7, we get the 5. 6 and 7, we get the 6. Now at that point, what happens?
Well, we're out of one array.
We've exhausted the first half, and so we can just copy down the 7 and the 8. Or, well, put it this way. Okay, we've got to copy everything back to where it came from. So I guess we don't have to copy the 7 and 8 down. We can leave the 7 and 8 where they are and just copy everything back up. Okay? But the point is, you have to do something special when you run out of one array. You stop merging at that point. So here is the worst case. We just said 2 recursive calls, each half as big, plus linear time. And we get the bound as O of n log n. Okay? And in fact, it's always n log n. The worst case is always n log n, so it's theta of n log n. What about the best case for quick sort, for merge sort? What is the best case for merge sort?
Sorry.
Yeah?
N log n, is it always is going to be splitting and attempting to sort?
Yeah, it turns out, he said it's n log n. Same thing happens. It's always doing the split, always making the recursive call. There's really no difference between the worst case and the best case. But let's see if we can improve it. There's a small change we can make and turn the best case for merge sort into linear time. You got your hand?
I was thinking, like, we learned about blended algorithms, and you can use, like, insertion, like, on small elements.
Sure, we could cut over to insertion sort or selection sort, but that might improve the constant, but it's still going to be n log n. Yeah?
Check to see if it's sorted already first.
Well, you can say that about any algorithm. You can check to see if it's sorted, and if it is, do nothing. But that could be a fairly expensive check to make. It's a linear check to make. There's something that scales better than that I have in mind. Yeah?
If you do the check while you're splitting, each time you split, you do this.
Okay. No, it's not. We don't do that. We're not. It doesn't involve checking to see if it's already sorted. It involves improving merge or avoiding the merge. Yeah.
Once you get it down to like a certain number of elements, like then you want to do a quick sort, right? Like once you get to a certain
Well,
like,
right. Well, okay. Again, cutting over another algorithm might make the constant faster, but it's still n log n. When we did Recursive, blending didn't increase the. Recursive and the blended multiplication algorithm have the same asymptotic complexity. It's just that the constant is lower. Yeah?
Could you check if the first element of the second array is greater than the last element of the first?
Exactly.
Array?
So what she said is, take that array right there, and let's see if I've got it here. We check to see well, I have it in the opposite sense. If the last element of the first half is greater than, when you get ready to merge, if the last element of the left half is greater than the first element of the right half, then you do the merge. Otherwise, you don't. Okay? So how can you skip the merge in this case? Yeah?
each subarray is already in order, and because the biggest element in the left array is smaller than the smallest element in the right array, you know that they're already in order.
Exactly. So look up here. Suppose you're having to merge that, the 1, 2, 3, 4 with the 5, 6, 7, 8. You check, you find 4 is less than 5. So the array's already in order. By one comparison, you can tell that the subarray that you're sorting is already in order. Just by looking at the last element of the first half, which is going to be the biggest element of the first half, and the first element of the last half, which is going to be the smallest element of that one. So, how does that affect the best case? How many recursive calls are we making in the best case now? Still making 2. Still half as big. But what's the overhead beyond the recursion now in the best case? Constant. We just do the single comparison. So we get that, and that works out to be linear. And this has the advantage if it works anywhere in the recursion. If it turns out that a subarray has a property, you're going to benefit not just at the top level, you'll benefit at lower levels as well. So it can improve not just the absolute best case, but cases where the array is pretty well ordered to start with can be improved this way at the cost of a little bit of extra comparison. Okay, so that's an idea. All right, let's look at quicksort. So here, we'll look at quicksort. I'm going to introduce an idea first before we look at quicksort. This is GCD. So this is a recursive implementation of greatest common divisor. We say if B is 0, return A. Otherwise, we compute the mod of A and B, and then we return the result of this recursive call. We call GCD on B and mod. So that's just the GCD algorithm written recursively. Now we know you can write the GCD algorithm using a loop. Here I've written it recursively. There is an optimization that can be applied to certain recursive algorithms. In some languages, the compilers will take a recursive method and apply this optimization automatically. And the optimization essentially returns recursive calls into loops. And the optimization can only be applied when the recursive call is the last thing that the method does. Right? So right here, the last thing this method does is call GCD, and whatever is returned by the recursive call is returned by this method. That makes it tail recursive. If you return immediately after the recursive call returns, don't do anything else, then it's tail recursive. So is merge sort tail recursive? No, because after you get there are 2 recursive calls, but as soon as the second one returns, then you merge. You're doing something before you return. So merge sort is not tail recursive. What about those majority algorithms you looked at? Are they tail recursive? No. Once they get a return value from the recursive calls, they've got to do some counting. But this one is. Because literally the last thing that happens is we just return whatever the recursive call returns. So that's tail recursive. This is the optimization you can make. So a compiler can mechanically turn this into this. And what we do is we say, so this green thing here identifies the base case. So we negate the base case and make a while loop instead. Then whatever the base case returns, we copy it down below the while loop. Then we take all the stuff in the else part, the recursive part, that isn't the recursive call, and copy it into the while loop. And then the last thing we do is we replace the recursive call with an assignment to the parameters of GCD. So we're calling GCD with B as the first parameter and mod as the second parameter. So we replace them over here by saying A gets B. So first parameter is A. So we assign B to A and we assign mod to B and then iterate. And we do that loop there until B becomes 0. So what's going on here? Yeah?
It looks like we're going to lose our stack trace if we ever...
Okay, he said we're going to lose our stack trace. So let's think about that. When we make recursive calls, how do we keep track of the new values of A and B? We keep pushing stack frames. So we have an initial call and A is something and B is something. Then we make a recursive call. It has an A and B with different values. Another call, A and B with different values. Another call, A and B with different values. Another call, A and B with different values, and eventually we hit the base case. Then we return the same answer all the way down. Okay? here to keep track of A and B? All right, what are we doing to keep track of A and B?
We don't, we just keep the latest value because it doesn't really matter what the
Okay.
value of A and B is.
So when we compute new A's and B's, we just, the new values of A's and B's, we just store them into the parameters, A and B and loop. So we just reuse the current stack frame. Rather than creating a new stack frame and storing A and B there, and then another stack frame, store A and B there, we just keep reusing the same one. Why can we reuse the same one? Yeah?
Because we're only interested in the latest values of A and B.
He says it's because we're only interested in the latest values of A and B. There's another way to put that. What is it about tail recursion that guarantees that once you make the recursive call, you don't care about the old values of the local variables?
Because you don't do anything with them.
Because by definition, in tail recursion, that's the last thing, you don't use them after that. That's what tail recursion means. The last thing you do is just return the resulting recursive call. So rather than using a bunch of stack space to store values of A and B over and over again, we just keep reusing the same stack frame. And we replace a recursive call with an iteration. Now, it can be difficult to see at first, but it's actually, it's a mechanical, a very simple optimization that a compiler can do.
How much faster is this?
Well, how much faster is it? Are we changing the number of mods we do? Right, it's the same operations are occurring in the same order. But what the only difference is, over here, we make a recursive call which involves allocating a stack frame and copying the parameters up. On this side, you don't create the stack frame. You just store the parameters in the same stack frame. You reuse A and B. So if you do the asymptotic complexity analysis, it's the same. It's not, the loop will be slightly faster because it doesn't have to push and pop stack frames. So what's the payoff? Yes?
You reduce the coefficient on your algorithm?
Well, you're reducing the leading constant slightly.
Yeah.
But there's a more important payoff, yeah. It saves memory. This one takes constant space. This one is using space on the stack. It doesn't run in constant space. Now, that may or may not be a big deal. You may not be using a lot of stack frames, but sometimes it is a big deal. So how can you recognize tail recursion? If I give you a method and ask, is it tail recursive? What will you look for? Yeah?
If the recursive call is the last thing in the method?
Yeah. The last thing you see, the last thing after the recursive call, you just got to make sure that what the method does is return. Yeah?
So in some of our previous examples, there were 2 recursive calls. Does that throw out the possibility?
Okay, suppose there's 2 recursive calls. First it makes one, then it makes another. Could that first recursive call be a tail recursive call? No, because something happens after it. We make the voice is changing. Something happens after it, namely the second recursive call. But that second recursive call could be tail recursive. So you could apply the optimization. The first recursive call would still be recursive, it would still be there. But then the second recursive call would be replaced with a loop. Okay? So let's look at such a quicksort is such a method. So there is quicksort. I claim that that second call to quicksort, the second recursive call to quicksort, down here and right here, is tail recursive. Why is it tail recursive? Okay?
Because the output of quicksort is a call to quicksort.
Okay? We call quicksort. We call this, make the second recursive call. It returns, and then what do we do?
We call quicksort.
No. After this second call here returns, what do we do?
We're done.
We're done. We return. So that is a tail recursive call. And it could be replaced with a loop. So just to remind you how quicksort works, we pick a pivot. In this case, I'm going to pick the last element as my pivot, 4. And then I scan through the array, starting from the left, and I'm looking for something smaller than 4. I'm sorry, something bigger than 4, and I found it in 6. Then I scan from the right, looking for something smaller than 4. So I'm trying to put the things smaller than 4 to the left, things bigger than 4 to the right. So what do we do when we find that thing bigger than 4 and the thing smaller than 4? We swap them, and then we continue scanning. So now we're looking for something bigger than 4. That's not, that is. Then we scan left, looking for something smaller than 4. We find it. Now, at this point, when the scans have crossed, we know that the partitioning is over, and what do we do instead of swapping 5 and 2?
Swap 5 and 4.
All right, we swap that 5 with the pivot. And now we know everything to the left of 4. 4 is where it needs to be, and we have to sort now. Let me just go back here. I'm just recoloring. We sort the things to the left of 4 and the things to the right of 4. So we recursively sort one of the halves, we get that. We sort the other half, we get that, and we're done. There's no post-processing up to that second recursive call. That's what makes that second call tail recursive. Now, how does the analysis, well, here's the tail recursive optimization. I'm trying to remember how my slides work. So, I'm claiming we can mechanically go from up there to down here. So notice that we take the negation of the base case. The base case doesn't show up here explicitly. So the negation of the base case is just the high minus low is greater than or equal to 1, which is the recursive case. So we say while high minus low is greater than or equal to 1, we partition we do the partition. Then we recursively sort the low half. And then rather than make a recursive call to sort the high half, we just reset low to be pivot plus 1 and loop. And so that iteration will now be sorting the high half. And it'll sort the high half by recursively sorting the low half of it and then looping to sort what's left on the right side.
But then your while loop only runs twice, right?
Say what?
Your while loop only really runs twice?
No. Let's draw a picture and see what the while loop would do. Trash that. Okay. Let's say we have big old array. So how do we sort the first half now? So let's say each time we split it exactly in half. How will the left half be sorted? Right, we make a recursive call to sort that half. Okay? We split it in half. How will that be sorted? We recursively sort that half. Then we recursively sort that left half, and then that left half, and then we're done. And then we return. What do we do about the right half here?
Where you sort it iteratively?
Yeah, we loop, and it'll sort the right half. Okay? And that right half will make some recursive calls. The point is, you're still doing recursion, just not as much. Like when it comes time to sort this thing, it'll make recursive calls to sort the left halves. But you end up eliminating half the recursive calls and replacing them with the loop. I understand it can be hard to see, so I'm not sure what I can do to convince you that it works right now. Except, what I want you to recognize is we've done the standard tail recursion optimization. You really have to work through this yourself with an example to see what's happening. But I've replaced one recursive call, this one, with code that resets the parameter low to pivot -1. The other parameters haven't changed. A and I are the same, and we just loop. Yeah?
So I'm confused. Just instead of the while loop's condition, it should be the negation
Of the base case.
So it looks like it's just the same thing as the if statement.
Well, that isn't the base case condition.
Right.
So it's either, you can think of this as being the negation of the base case or the recursive case condition. Because the negation of the base case is the recursive case. Right. In the first example we looked at, we had the base case condition appeared, and the recursive case was just else. Here, the recursive condition appears, and then there is no else. So while we're supposed to be doing recursion, loop instead. Just reuse the current stack frame. So let's analyze this. Okay? So what is the time complexity of quicksort here?
In the best case,
Let's see what I want. What's the worst case of quicksort?
n squared.
Well, let's write a recurrence relation. What would be the recurrence relation for quicksort? Yeah?
T of n equals 2 times n over 2
Okay? So I did that to, I couldn't remember if I'm analyzing the original. The original analysis would look like merge sort. Well, in the best case. But in the worst case, what is the worst case for quicksort?
It's a shorter array.
That's when you do the partitioning and everything is to the left of the, everything's to the left or to the right of the pivot. And so you just reduce the problem size by 1 each time. And so you end up, you know, the next level recursion is t of n minus 1, and then t of n minus 2, and then t of n minus 3. I left out the dots there. But that just adds up to the, it's n squared. Oh, I see what I'm doing here. In the worst case, to sort an array of length n, we make a recursive call of size n minus 1, and a recursive call of size 0. And then we do a linear amount of work doing the partitioning in the first place. And so it works out to n squared. Yeah?
So is b just 1 in this case, when we're applying the master's theorem?
Well, we can't, he's asking about the master theorem. You can't apply the master theorem in this case. Well, someone tell me why I can't apply the master theorem in this case. Yeah?
You're not creating an equal size of subproblem.
Right. I'm not splitting the problem in half or third or a quarter or something. I'm just subtracting 1, so the master theorem doesn't apply. Okay? We're overdue for a break, so let's take a break for a few minutes and we'll finish this up. All right, let's get started again. All right, so to come back to this, I'm sort of doing the time analysis up there. I mean, you know the worst case is n squared. Someone tell me what is the recurrence relation for quicksort in the best case? Yeah. How many recursive calls? Well, look at the code. How many recursive calls do you see? 1, 2. 2 recursive calls. In the best case, they're each going to be half the size of the original, plus a linear amount of work to do the partition. So that's your recurrence relation. So just like merge sort, that's n log n. Yep.
How do we analyze the tail version of this? It's kind of tricky.
Okay. So he's asking, how do you analyze the tail version? Okay? Because I only see one recursive call. What's the short way to, if you know the time complexity of the original version, how can you obtain the time complexity of the tail recursive optimization? Well, he's saying you take out one of the recursive calls, but then it's kind of complex because you got to deal with this loop. What's the easier way?
Is there a way to reverse our tail optimization?
Yes.
Aren't they the same in speed in general anyway?
Exactly. It's the same. Tail recursion just helps with memory consumption. It'll make it a little bit faster, but not asymptotically faster. Just changes the constant. But and so you just analyze the recursive version, and that gives you the asymptotic complexity of the tail recursive optimization.
And then you gave us a tail optimized version, and
sure, if you started with this, maybe you could recognize it and unoptimize it, so you could use the master theorem. Okay, so these analyses apply to both versions. Now, what about space? So let's think about space. Now, where is the space consumption in quicksort? Where's extra space consumed beyond the array you get to start with? Some local variables. Okay.
the activation record.
Right. So your stack frames. Now, in the worst case, how many stack frames will be used? Forget about the tail recursion optimization. What can happen in the worst case in quicksort? How deep could the stack come?
N stacks.
You could have the n stack frame. So you start with an array of length n, you make a recursive call for n minus 1, another recursive call n minus 2. You end up with n stack frames stacked up before you start returning. If you're talking about a million element array, then you're talking about your stack consuming a million stack frames. And a stack frame is going to have room to store the local variables. So the stack frame is going to be, 40 bytes, let's say. That's 40 megabytes just for the stack frames, which could easily blow the stack, depending on how your settings are. And if it won't, then make a billion element array, and you're using 40 gigabytes to sort the billion element array. That's not good. We'd like to do something about that. Now, in the best case, how deep does the recursion get? How many stack frames can be pushed before any returning starts? Okay, someone said log n. Yeah, in the best case, array of size n, then you make a recursive call that's half as big, half as big, half as big, half as big. You're going to bottom out after log n steps. So now if you sort that billion element array, how many stack frames are we talking about? 30-ish. Yeah. Log of a billion, log base 2 of a billion is 30, roughly. Okay. That's certainly manageable. Big difference between a billion stack frames and 30 stack frames. With the tail recursion optimization, let's see what we can do. So, what's the worst space consumption of the tail recursion version? Remember, it eliminates one of the recursive calls by looping, not creating stack frame, but the other recursive call gets made. So what's the worst thing that could happen? Okay?
Back to before. It's still in here.
We still got the problem. Because look what we're eliminating. We're eliminating the recursive call to the high half. We're keeping the recursive call to the low half. Well, what if the low half consists of all but one element? The high half is empty, and the low half consists of n minus 1 elements. And suppose that continues consistently all the way. So you've offloaded almost none of the work onto the iteration. You're still going in stack frames deep. So let's just switch. Why don't we do this one first and do the tail recursion on the low half? Would that help things? Yeah?
Wouldn't your worst case still be the same?
Yeah, and the worst case will be the same, because then there could be a situation where the partition is such that the high half is all the elements but one, and the low half is empty. So it seems like we're in trouble either way we go. Still taking all those stack frames in the worst case. How could we improve upon this? Which half do we want to do recursively? Yeah?
We want to do the smaller half recursively.
We want to do the smaller half recursively and iterate on the bigger half. Okay? The smaller half is guaranteed to never be bigger than half the array, right? And so if we're always making the recursive call on an array that's at most half as big, we can't get more than log n stack frames deep. Well, how can we arrange? You know, we got to do one or the other. How can we arrange so that we're always making the recursive call on the small half and then looping on the big half? Yeah?
Every time you check, and then for the bigger half, you'll
Okay.
just switch high or low to the pivot plus or minus 1.
Right. So we do that. We just check which half is bigger. And we make the recursive call on the smaller half. Reuse the stack frame for the bigger half. Now, the worst that we get is log n stack frames deep. And it's possible to use constant space if you get into the situation where you're taking n squared time. It turns out that you're just using constant stack space. So that's some consolation, I suppose. So by doing this check, we make better use of our resources. We can guarantee that quicksort will never hit that worst case of running out of, blowing the stack. Doesn't do anything for the worst case running time. It does wonders for the worst case space consumption. So you think you understand an algorithm pretty well. There's always folks that have gone beyond that and thought about small details like this, which can be important in practice. Yeah?
How did you get the best case space complexity of constant?
Well, what will happen now if you get an array that's already sorted, and we do the partitioning, and the left half has all but one of the elements, and the right half is empty? Which side will be, the recursive call will be made on which half?
On the T one.
On the empty half, which will return immediately. And then we'll iterate. And then it'll make a recursive call on another empty half. That'll return immediately, and we iterate. So we never have more than 2 stack frames. Because recursion can't go very deep. Okay, now, let's take what we know about quicksort and look at the selection problem. So this is a divide and conquer algorithm. Given an array A of length 3, I want to find the element that would be at A sub I if A were sorted. So for example, let's suppose the array is of length 100 and I is 99. I say, give me the element that would be at A sub 99 if A were sorted. What would be a quick way to answer that question? No, the specialized one. I ask, if you got an array of length 100, I want to know what would be stored at index 99 if the array were sorted.
You just pull 99, right?
Do I sort the array and see what's at index 99? Can you think of a better way than that?
So you pick a pivot, then you move.
Yeah.
Second largest. Yeah, could you sort it in descending order, and as soon as you find a second number, take that?
I don't want to sort it at all. There's got to be a better way. I want to find the element that would occur last in the array if the array were sorted. Yeah?
You start sorting it, but as soon as you reach the spot where what you're looking for is sorted, you stop sorting and just return.
Well, sort of, but there's a much simpler way to put it. Yeah?
Just find the largest element.
Find the largest element. Make a run through the array. Find the largest element. That's the element that would be at the last index if the array was sorted. And what if I ask you for what would be at index 0 if the array was sorted? You just find the smallest element. That's easy. Now, what if I ask for the element that would be in the middle? Then you might think that you need to sort it and then see what's in the middle. Okay? But it turns out we can do better than that. So that's the selection problem. Sometimes it's easy to solve if you're asking for what would be at the extremes. Sometimes it's not. So here's an approach based on quicksort called quick select. So the idea is you're asked to find, given an array A and a low and a high index, find the element that will be sorted at index I if that chunk of the array were sorted. And it's the same idea behind quicksort. We do a partition on the subarray. And if it turns out that the partition returns the index where the pivot goes. If it turns out that the P is I, in other words, the pivot is stored at index I of the array, why can't we just immediately return that as the answer? What's the one thing you know about the pivot after you partitioned? Yeah?
That item is sorted.
Well, he says that item is sorted. The way I would put it is that item is where it's supposed to be in the final array. The pivot, after you partition, the pivot will never move again. It's in the right spot. So if you've asked for what's at index I, and lo and behold, the pivot ends up at index I, there's nothing more to do. We found the answer. Otherwise, we make a recursive call depending on the relationship between the pivot and I. So what if the pivot is greater than I? We're looking for something that will be index 5 if the array is sorted, and the pivot is index 10.
You run it on the...
Right, we don't, where's index I going to end up? If the pivot's at index 10, we care about index 5, does the high half of the array matter? It's not going to contain index 5, because the pivot's at 10, so we throw away the high and recursively do our selection on the low half. And we gradually hone in on the pivot that way. So it's kind of like binary search. So partition, look at the pivot, and there are three possibilities. Either you find what you're looking for, or you recursively deal with the low half, or with the right half, but not both. Okay? So let's see how that works. What's the answer going to be? Quick select on A of 4.
4, right? 'Cause
What would be stored at index 4 if the array was sorted? Because we've got the numbers 1 through 8. Let's see. What will be at index 0? 1. So index 4 is going to have a 5. So the answer will eventually get 5. So I did that too. So 4 is the pivot, and I'm just showing you the partition's happening all on one thing. But after the partitioning, 4 ends up there. We got 1, 3, and 2 to the left, and the other things to the right. So what's our, what do I do at this point? Our pivot is at index 3. We're looking for what will be stored at index 4. So what do?
you run quick select on the top half.
We run quick select on the top half to find out what will be stored. We're caring about index 4. So we throw those away. We throw away the pivot and the low half. Now we're dealing with the high half. When we do the partition there, we end up with this. 6 is the pivot. And that's the high half, that's the low half. We look at the pivot, and what's going to happen? Finger wiggled. Okay. Our pivot's at index 0, 1, 2, 3, 4, 5. We care about index 4, so what do we throw away? The pivot and the top half. And we're left with that, and if the algorithm will run once more, the low will equal high, so we'll hit a base case. And we'll return 5 as the answer. So that's quick select. Yeah?
Just correct me if I'm wrong, this works because we're using integers for this, right? If we were to use just any generic element, we couldn't.
No, he's saying this works because we're using integers. No, it works because it works on any element that can be sorted. The index will be an integer. That's necessary. But the elements don't have to be integers. They just have to be sortable. So strings, whatever. What's the complexity of this?
In the best case?
Let's see. Okay. Let me see real quick here. Best case. Okay. So what is the best case for the algorithm? There's a hint up there.
You run it once and
You don't even have to make a recursive call. You partition it and you look at it. The pivot is what we're after. And so it's just the cost of the partition. Okay? Now, what's the worst case if we always are lucky and the array gets split in half? It always gets split in half. What's the recurrence for that?
and plus a half.
Someone besides Anthony. Too many answers from the front. Yeah? Well, tell me the recurrence relation. Still. Yeah?
The Tn is equal to 1 Tn over 2.
Okay. Plus.
Plus the O of n.
Right. So to solve the problem of size t, we're making one recursive call. I said here we're assuming there's always a perfect partition, so we get n over 2 plus, where's the O of n come from? The cost of the partition. Okay? So that's sort of the worst case. It's not really the worst case, but it's the worst we can do if we always get a perfect partition. And that turns out to be O of n if you use the master theorem. Now, what if you get very unlucky and the partition is always as bad as possible? So you do the partition and you end up with an empty half and then another half that has all but one element. It's no longer analyzable with the master theorem. You make one recursive call and it turns out to be all but one of the array plus the cost of the partition, and that works out to be n squared. So just like quicksort has a bad worst case of n squared, quick select has a bad worst case of n squared. Yeah?
Can you say that's over 1, so b equals 1? Or does
What?
b have to be?
Okay, so you're talking about this here?
Yeah.
Okay, what's the question?
Can you say t of n minus 1 is over 1, so b equals 1?
Oh, no, b has to be greater than 1 for the master theorem. You have to be reducing it by a sort of a divisor other than 1. Yeah?
In the recurrence relation, where does a come from? I mean, I know it's not on the recursion.
Right here?
No, you know how sometimes there's a coefficient in front of the t?
Right.
Yeah,
So
where does that come from?
it comes from the number of recursive calls we make. So when quick select is called, it's going to make one of these recursive calls. So that's the one. We make one recursive call. We're assuming each was half the size of the original. Okay? So we got that bad worst case there. Now, it turns out the average case, I won't go into it, but it's linear. Now, for a long time, people wondered, is there a way to get this down to linear in the best case? I mean, in the worst case, to avoid this n squared. And in fact, there is an algorithm. There's a sort of a famous algorithm for doing selection. We're not going to talk about it. It's not in the book. But if you got a chance to read about it sometime, it's just sort of mind-boggling. You divide things into fives. You end up creating sets of. So there's going to be a 5 in the master theorem, and it gets weirder from there. So there's a solution, but we're not going to talk about it.
Is there a name for that?
I'm not sure. There must be a name for it. I don't know the name of it. But it's the linear time worst case selection algorithm. tell you where we're headed now. So we've sort of, we finished up here with divide and conquer. What we're going to do next is prove that comparison-based sorting always requires n log n in the worst case. I imagine some of you have seen this proof before, 2420. Is that the case? Who has seen it before? All right. A couple people. All right, oh well. So we'll show that why, we'll prove that no matter how clever you get, any sorting algorithm you devise that works by comparing elements requires n log n in some case, n log n time in some case. And then we'll move on to graph algorithms, which is chapters 3 and 4. Okay? So we'll, rather than start and work for 4 minutes, we'll just stop here.